Good. So, hi everyone again. So, as anticipated this morning, I will tell you about searches for transient sources with Cherenkov telescopes. So, these are the instruments that are currently operative right now. Cherenkov telescopes. Well, we have Veritas in Arizona for telescopes 12 meters, HES in Namibia for telescopes of 12 meters, and one gigantic 28 meters telescope. And then in La Palma, we have the two Magic telescope, 17 meters of diameter, and then the first prototype of large-size telescope of CTA, LST1, 23 meters of diameter. So while HES, Magic, and Veritas are operating since almost 20 years, LST1 is much younger. It started operating in 2019, and now we have the other three LSTs that are under construction. I will show you a slide at the end. And so what we do with this telescope is to detect gamma rays in an indirect way. The threshold is variable depending on the size of the telescope. And so, for example, with the LSTs, we can go have a threshold of tens of GeV. So why we can study transients well with ECTs? Well, because they are sensitive. So usually sensitivities for ECTs are given with observation time of 50 hours, which for transient doesn't really make sense. Usually, for example, for GLBs, you have only one shot, and maybe you observe for minutes or hours. So the plot on the right gives us more information. So this tells that with Cherenkov telescope, you can get enough photons even in a short period of time, so that you can get very nice spectra. Maybe you can do time variability studies and so on. So this slide is mainly for gravitational waves, since ECTs have a very small field of view compared, for example, to the localization that we get from gravitational wave interferometers. So you don't know really in our field of view where the source could be. So what you want is to have a sensitivity that is quite the same across all the field of view. So, for example, this is for the figures that are expected for CTA, northern array and southern array. So what you can see is that the sensitivity is good all across the field of view. Of course, there are challenges. As I said before, we need to point whatever we want to observe because our field of view is limited. So we need someone else giving us coordinates. And so here it comes into play, for example, the GCN, all the system that we were talking about earlier. So we get from Swift, from Fermi, from LIGO, Widman, Kagra, and ASCII, we get the coordinates about the different kinds of alerts. Of course, this introduces a delay because we need to get the alert, then we need to repoint. But yeah, in best cases, we can be there also within a minute or so. Also, usually transient can be distant. For example, GLBs, redshift of 2 or whatever. So for us, it's not good because the gamma rays gets absorbed on their way, especially more absorbed if the more the distant is the source. Our duty cycle is limited. We observe only during the night when the weather is nice, when there is really not strong moon and so on. So this means that we cannot really be there always to observe something when it happens. And for example, as I said before, large localization. So we need to find a way to cover large regions, which usually is done by doing some tiling of the regions that we get. So how can we face these challenges? How can we tackle them? Well, for example, first of all, to get the coordinates, we need some kind of other system that is connecting to the brokers and getting information from them. So these can be used to implement strategies of follow-up and then maybe having an automatic reaction of the telescope. Then we need to be able to repoint fast. So for example, in the case of Magic, this fast mode is 7 degrees per second. For LST1, it's 10 degrees per second. So we want to be there in less than 20 seconds from any source that we are observing at the moment. And actually, being the operations coordinator of LST1, I get some perks. So for example, I will show you something that we did in July about the fast repointing test with LST1. So there is no sound, but okay, that doesn't matter. So you have to imagine that LST1 weighs 100 tons. So something that moves at 10 degrees per second, it's quite impressive. So I think at the first Astro-COLIBRI workshop, I showed Magic, but that was quite old. This is just 2 months old, basically. So I didn't include in the slides because at some point there will be a press release, possibly. So yeah, that is how it looks like. Of course, during the night you cannot see much, but this was at the sunset. So this was really cool to see. And also to tackle the problem of AVL absorption, you need to have the lowest energy threshold that you can possibly get. And so, for example, with LSTs, in this case, you have to have a big telescope. You can go down to 20 GeV or less. And MAGIC also somehow and HESS can go also to similar energies. And then somehow on the lines of what Dave said before, we also need to have some decision taking. So for online decisions, so when the alert is happening, usually the operators on site, they call the so-called post allocate, and this person has to decide what to do with the alert. So see the incoming information, then maybe sometimes we need to drop the observation if, for example, we see that the gamma ray burst, in this case, it's at too large redshift. Then we have, of course, some real-time analysis telling us, okay, is there a detection of the event or not? So this also gives us information if we want to continue or not the observation. And finally, we have also fast offline analyzers. So they get the data the day after and they perform the analysis and then they see if there is something into the data, because of course, the real-time analysis, it's not as sensitive as the offline analysis because it needs to be fast. So talking about other system, since I'm involved in the one of LST1 and MAGIC, I just put here like a scheme of what it does, but basically it's really simple. It has to get the alerts that we get in this case from GCN, but also other brokers are possible. And then it implements the strategies that is decided beforehand by us. So for example, visibility, constraints, and so on. And then if the criteria are fulfilled, analysis is sent to, in this case, to the telescope control unit, which triggers an automatic reaction of the telescopes. MAGIC has a similar system, I know, because I also maintain it. And also Veritas should have one, as far as I know, at least I was in contact with the person implementing it. And actually the S1 is also a bit more sophisticated. You can see more details in the paper that they have, because it's a really full-fledged TO system. So it really talks with the scheduler system, with the telescope control unit, and so on. And then, of course, okay, I talked about strategies, technical details, and so on, but okay, so what are the results that we can get with all this work behind? Well, in this case, for GRBs, you can see these are the GRBs that have been detected so far at 5 minutes. I thought we were saying 5 GRBs, but okay. So, which is indeed true, but with love. Okay, so these are the 4 that were detected by Cherenkov telescopes. Actually, on the left and on the right, HESS and MAGIC respectively. I cannot go into the details of the results, but I guess that many of you know already about them. And actually, the other one that was also shown by Deidre, the boat 221009A. This was actually shown last week, 2 weeks ago at the Gamma conference in Milan. So here you see the first points are the one by LASO, so extensive air shower. So they get the nice onset of the afterglow and then the decaying phase. Then there is HAWK, which unfortunately, I mean, the source was not in their field of view when it happened. It happened like 6 or 8 hours later, so they get only upper limits. And then we have the points by LST and HESS in purple and red respectively. And actually for LST1, even if we observed with very strong moonlight, because of course it happened when we were not operating due to the moon break, still we could follow up basically a bit more than 1 day after, and we have a hint of 4 sigma on the first day. And you can see that basically LST1 upper limits are bridging the ones between HAWK and HESS, and they have a similar level between the two Cherenkov telescope. Actually, HESS has a dedicated paper about this with their data and interpretation, so I left there the reference if you want to have a look. So going to gravitational wave, I think this one is a nice example of how strategy implementation can give you really nice results. So even if there was no detection, the strategy that has implemented at the time allowed them to basically to observe the region where the source after found out. So this SSS 17A already the first pointing. Of course, then they observed the 2 that are shown below, but the first one was the one where the source actually was. So this is really showcases how strategy can be important in this case. And of course, with LST1 and MAGIC also, we are also implementing something like this. So having a tiling of the region Actually, we are using this type I code that I think tomorrow Ali will present. Very quickly, also neutrino sources. I guess this will be shown also tomorrow by Eric. But yeah, I think this is one of the most important cases, TXS 0506, where we had first the neutrino detected by IceCube, and then there was the detection of gamma rays by Fermi, and then after by MAGIC. Actually, there are also other neutrino sources, so like NGC 1068, for example, MAGIC for that has 150 hours of observations, but with no detection, which in any case tells something about what's going on to the source. And I think there is another one, PKS 1424, but I don't remember if, for example, for MAGIC or has data about the source. This I don't remember. And actually talking about platforms and sharing data and so on, typically ECT collaborations are kind of closed and they have private data. But you know, CTA is coming, it will be an observatory, so the policy will be similar to the one that Fermi has. So basically sharing whatever is taken as the data and the results that we get from that. So for example, there is this nice initiative by Hess, and they are sharing basically the observations that they do about the gamma ray burst. I don't say in real time, but basically soon after they either schedule or perform observations. Actually, I see that Mathieu, you are in almost all of them. And actually, Hess allows external people to submit TOs. So people can submit the TOs, and then these are evaluated and guest observation can be scheduled. And then there is also the part about sharing the data in this so-called data level 3, which is defined by CTA, which is a FITS format. You can see more about that. So for example, there is, okay, it is not about transits, but for example, for Hess, they have this huge data set about the galactic plane survey, which is very nice. So people can get the data and play with it and maybe do some science. And so, yeah, this gets me to my summary. Of course, I couldn't talk about everything. So for example, faster burst, galactic transients. I guess that many of you are waiting for this T Corona Borealis and so on. I couldn't talk about that. So yeah, apart from what I said just now, I wanted just to show how it's going on La Palma. So you see here from right to left, we have MAGIC 1 and MAGIC 2. So they are since 21 years now. Then we have LST1 in the center, which is operative since 2018. And then on its right, you have LST4. Actually, you could see that maybe you can tell that LST4 is finished, but it's not. I mean, it's missing the mirrors, it's missing the camera. These will come, actually the mirrors will come next month, camera later next year. And then you have the other two telescopes, so LST3 and 2, that you can see they have the structure, but they are missing the arch and then everything else. But yeah, it's going pretty fast with respect to the beginning of this year. The landscape changed quite a bit. So if you get the chance to go to La Palma, have a look and you will be amazed. Thank you.